need to like hand in next week. I'm cryptic on the board because I didn't want you focusing on that while you were brainstorming controlled variables. All right, so this is all going to have to be typed. I want your research question, right? So your research question should be something like to identify a mathematical relationship between the two things that you just handed in. So that stands for research question. I need a table that identifies all of your variables, the independent variable, the dependent variable, and then all the things that you said you need to control. Okay, I need your full procedure. Your procedure needs to be telling me exactly what trials you're doing. And then I also want an electronically generated diagram that shows your setup. So this should be something that you create yourself. It doesn't have to be ultra complex, but IB very clearly wants you to make your own diagram showing your setup. You don't have to have blank tables that your data would go into, but some folks like to do that. You don't have to do that though. But those are the 4 things that would be due next week. Follow-up questions from anybody about what I'm asking you to generate for next week? Yes?
The table with all the variables, does it have to have the methods of control in the table?
Great, so does this table have to have how you're going to control them? It can, but it doesn't have to. That could just be in your procedure. Other questions? Okay. We may or may not carry out your designs. It's not definite that we will, but hopefully you're designing something that could be carried out with the equipment that I have or with equipment that you have yourself. All right, so last class we just very briefly said what topic 6 was about. So topic 6 I thought was called forces and fields, but then I think somebody corrected me and said it was called fields and forces. And we did say that there were 3 types of forces and fields that we're going to care about. In topic 6.1, we're going to care about gravitational forces and fields. In 6.2, we'll care about electric forces and fields. And then in 6.3, we'll care about magnetic forces and fields. And these really are our only 3 examples of field forces that we talked about last year, right? So these are all of the types of classic fields that we discussed in physics. And I'll tell you a little secret. I used to hate this topic. It was like my least favorite topic to think about and to teach and to write questions about. And I was able to make myself like it a few years ago. Once I started to try and educate myself on some of the kind of modern areas of physics. In particular, something called quantum field theory. So what I'd like to do is read you a very brief excerpt from an article written for physics teachers. It's actually called Teaching Elementary Particle Physics, Part 1. But I'm just going to read a very brief statement which kind of opened up my eyes a little bit to why this stuff is actually pretty cool. All right, so bear with me. It's kind of the end of this that is where I think it becomes kind of enticing to want to know more about these fields. All right, so this starts off. As Steven Weinberg has said, Steven Weinberg is like Nobel Prize winner, kind of famous for moving to University of Texas, Austin in the 80s and demanding that they pay him as much as they paid the football coach. So as Steven Weinberg has said, the basic ingredients of nature are fields. Particles are derivative phenomena. Students should have already learned about ordinary fields earlier in the course. Well, that's what we're going to be learning about now, right? So this is the reason I think it's good to learn about this. Remind them that fields are spread out over a region of space and that this region needn't contain any matter or anything at all. A field is a condition of space, a kind of stress in space. For example, there is an electric field at any point where an electric charge would feel a force, regardless of whether there is any charge there to actually feel a force. And remind them that fields are physically real as energy and momentum. We know this because when We know this because we know that they carry energy and momentum. For example, if I send a radio signal to Mars, its journey might take 20 minutes. But radio signals transmit energy from source to receiver, right? It's like our radiant energy. If energy is conserved, that energy must have been somewhere during those 20 minutes. Where was it? The answer in the electromagnetic field that carried the signal. This argument persuaded Maxwell and Einstein that fields are real. A similar argument applies to any force that is transmitted non-instantaneously. So that all probably wasn't very interesting because we aren't very comfortable with these fields that are being described here. All right, so here's where it becomes, I think, a little more interesting. The central notion of quantum field theory is that the universe is made only of fields. It's an odd idea. Viewed microscopically, the desk in front of you is a configuration of quivering fields similar to the invisible force field surrounding a magnet. When you slap the desk, go ahead, when you slap the desk, right, your hand does not pass through the desk because at short distances, the fields that are the desk repel the fields that are your hand. All right, so this quantum field theory is telling us that, matter is not exactly meaningless, but matter is an artifact of the fields, right, that are interacting. So electric fields, magnetic fields, gravitational fields, like that's all that we are. We're not matter, we're not solid things, we're just fields, right? So that, and this is like an accepted thing, right? This isn't just like some cockamamie theory that everything is made up of quantum fields, right? It's accepted. But we probably do need to be more comfortable with these classic fields that aren't so crazy in order to make more sense of the kind of more out there theories that have become an accepted part of physics. All right, so hopefully, well, that was able to convince me to care more about these things. This is probably one of the more abstract topics in the course, though, right? I do have a difficult time visualizing this field, this effect on space that things have that I can't really see. So anyway, that's my introduction to topic 6 that I chose not to try and cram into 2 minutes last class. Now, the thing I had up here when you came in was, what is Newton's law of universal gravitation? And I asked you not to look anything up. And I would wager that the vast majority of you did either write down or remember all or some of what we learned last year as Newton's law of universal gravitation. Yeah, right. However, I think there are some important features of this that you might not remember or we might not even have said last year. All right, so topic 6.1 has its entire basis in this law of universal gravitation. So we use this to find how much force exists between two things that are pulling on each other gravitationally. Let's pick 2 things to deal with, right? What do we want to use? We want to use the Earth, fine. And what else?
Jeffrey.
The Earth and Jeffrey. Let's not pick on somebody that's not here. Wait. An airplane. Fine. Alright, so we have the Earth and we have an airplane flying sort of high above the Earth. In fact, that would maybe be ridiculously high above the Earth. So the law of universal gravitation says that these 2 things are pulling on each other, right? And that pull is just due to their mass and how far apart they are, right? So this big G was our universal gravitation constant, right? 6.67 times 10 to the negative 11th. That's in your data booklet. I suppose we should probably at least make official what the units of measurement of this are. So that's what? Newtons Newton meters squared per kilogram squared, I think. Somebody back me up on that? I think that's right. Because then, right, if we multiply that by both of these kilograms, we cancel out the per kilogram squared. If we divide that by the distance, yeah, so that should be right. And that's in your data booklet, right? You don't have to memorize that. Now the 2 masses are just the mass of our 2 objects. So we have the plane, we have the Earth, A lot of times when we do have like a planet and then something that's much smaller, a lot of times we'll use a capital M for the bigger thing, right? So don't let that startle you if you notice that. And then R is the distance between the two things. All right. But there's a little more embedded in this law of universal gravitation that we might not have said last year. And most of that has to do with this R value. When Newton wrote this law, he said that this law applies to particles. Particles, as part of their definition, have that they don't have any volume. Right? So a particle, by definition, is a point in space. Zero volume. No volume whatsoever. All right, does the Earth have volume? It absolutely has volume. It has a huge volume. Right? The airplane, compared to the Earth, doesn't have much volume. But these aren't truly particles. They're not truly points in space. Now, if our two objects are sort of kind of far away, then this is fine. Right? If they have a significant volume, as long as they're kind of far away, like if the airplane is out here, then we could probably treat these two things as particles and it would be just fine. But if the airplane really is pretty close to the Earth, this might be a tiny bit problematic if we're trying to use Newton's law of universal gravitation. So you do want to somewhere, in the back of your brains, recognize that we are treating our masses as point masses. And again, if we have two things super close together, then that might be a bad assumption. If we have like the Earth and the Moon, then that's fine. Right? They're far enough apart that it doesn't matter that they have some volume. Another super important feature of this law of universal gravitation is that it is always attractive. Right? Gravity is only ever a pulling thing, not a pushing thing. And then remember that this was our first example last year of an inverse square relationship. So the distance plays a way more profound impact on the amount of force than the mass does. Or at least a change in the distance plays a more important role than a change in the mass. All right, so I think that's most of the things I wanted to review about this from last year. Follow-up questions from anybody before we go ahead and try and use this for a pretty complicated problem. All right, what do we have? About 10 minutes? All right. So what do we call that thing that takes all the pictures? No, the big one.
Telescope.
Yeah, the big one there.
Hubble.
Yeah, the Hubble, right. So let's, I want to do a problem involving the Hubble Space Telescope. Does that thing still work? Yeah, it's the Kepler one that looks for planets that doesn't work anymore. All right, so we'll get the Earth again, and I just want to use the Hubble Space Telescope instead of the airplane because it's quite a bit further away. All right, so here's the Hubble Space Telescope, HST. I would like to know what the weight of the Hubble Space Telescope is, right, out here. I want to know what the weight of this thing is. What kind of information do we need to know in order to calculate that? Robbie, what's one thing?
The mass.
We need to know its mass, and I'll give that to you. Its mass is 11,600 kilograms. What else do we need to know? Nick?
Mass of the Earth.
We need to know the mass of the Earth, yes. And that is 5.98 times 10 to the 24th kilograms. What else do we need to know? Justin? The distance between the Hubble Space Telescope and the Earth. The Hubble Space Telescope is 598 kilometers above the surface of the Earth. What else do we need to know? Elizabeth? We need to also know the radius of the Earth, right? In the law of universal gravitation, right, if we have point particles, then we would just automatically have the distance between them. But when we're using the Earth, right, we always use the distance between, well, when we use real objects, we use the distance between their centers, right, because we're pretending that the entire mass of the Earth is at a point located at the center of the Earth, right? We're pretending that. I didn't give you that distance. I gave you 598 kilometers above the surface of the Earth. So Elizabeth is right. We absolutely need to know the radius of the Earth. and that is 6.38 times 10 to the 6th meters. What else do we need to know? Yeah, that's it. I mean, we need to know the gravitation constant, but I think that's pretty much it. All right, so we still have 8 minutes. I think that's enough time for you guys to take 90 seconds and try and find this on your own, and then I'll get it on the board in another 30 seconds or so we can kind of check ourselves. Oh man, different units. Uh-oh. I'm getting something like 95,000 newtons. I think it might actually maybe have one more significant digit than that. 9.50 times 10 to the 4th newtons. That's quite a bit less than it would have at the surface of the Earth, but not orders of magnitude less. Yeah, Danielle.
I think that to the fourth, don't you have to change meters to kilometers?
Yeah, I think oh, no, you need the distances to be in meters. So I changed the kilometers one, the 598 kilometers into meters. Yeah, so you probably got like, what, 10 to the 10th or 10 to the negative second or something like that. Negative second. Yeah. No, we definitely want meters. Other issues with this? Yeah, I mean, this is the only thing that was difficult here besides the exponents was that, what Elizabeth reminded us of, that we do have to add in the radius of the Earth itself. So be on the lookout for that. That's really the only wrench that we would kind of throw in here. All right, so the next piece of this, right, that's all review really. The next piece of this is incorporating this concept of the field into our discussion about gravity, right? And I guess I didn't actually tell you what the objectives were. But one of our second objective in topic 6 was to define a gravitational field. All right, so the field, let me draw the Earth as we talk about this. All right, so here's the Earth, and because the Earth is so fat, right, it pulls on things that are in its vicinity. Right? Maybe the moon, maybe communication satellites, maybe Cliff's airplane. Right? It pulls on things that are in the vicinity of it. And it does that, we say, by establishing a gravitational field surrounding it. And sometimes we even depict that field with things called gravitational field lines, where we just point arrows in towards the Earth. We point them in towards the Earth since this is an attractive force, right? But we sometimes say that the Earth has a sphere of influence surrounding it. This is not the definition, right? We're building up to the definition. So the Earth is physically altering the space surrounding it to cause this gravitational force on things that happen to be there, right? It can exert this pull on things through empty space. That's why we called it a field force last year. So the gravitational field is recognizing that the Earth does physically change the space around it. I'm just writing that the space around the Earth is physically different with the Earth there than if the Earth wasn't there. Right? And then the gravitational field is the name that we have for the way in that the space is disturbed. All right, let's do the actual definition. The definition is quantitative, right? In fact, is there an equation in the data booklet for you? The symbol for it is a lowercase g. There's an equation in there, right, for topic 6? It's probably the second equation listed there. Nah? No, there's not? Oh, wow. All right, so this is a definition that we really need to know if they don't give you the equation. So the gravitational field strength is defined. Write this whole thing out.
It is that.
It is, of course it's there. So gravitational field strength, and this will be our kind of ending point for today, is defined as the gravitational force per unit mass that gets exerted on a small test mass that we place in the field. Right, so we shove a small thing right here. The gravitational field strength is defined as the force per unit mass exerted on that thing. All right, so let me write that down. Gravitational force per unit mass exerted on a small test mass placed there. Let me make sure that's consistent with what I had in the notes. Yeah. Exerted on a small test mass.
Is that game vocab quiz?
Oh, that's absolutely fair game for a vocab quiz next class. So I placed a small test mass here at A. Let me place a similar small test mass here at B. Are they going to experience the same force per unit mass? Starts with N. Heck no, we're not going to experience the same. Oh, look who's coming. Of course they're not going to feel the same gravitational field strength because they're not going to feel the same force, right? Newton's law of universal gravitation tells us the force is way weaker here than here. So the gravitational field strength is going to get smaller and smaller as we move away from the Earth. The Earth changes the space around it less and less as we move further away. I think that makes sense. So we still have a ways to go about becoming comfortable with this pretty abstract concept called the gravitational field, but that's our definition at least. All right, so we really did not get to a stage where I want you to have the extra questions that I was going to give you. So we are going to finish up the topic 5 packet. I don't know that I can tell you what pages that is in the next 2 seconds, but it's already posted on yesterday's blog out. We're finishing everything. No, I'm just pretending you're not here.